All right. In the last lecture, we talked about the effects of the maximum dissipation postulate, the consequences of it. And those consequences were primarily twofold. One, it demonstrated that the yield surface must be convex. And the second is that it demonstrated that the increment of plastic strain must be normal to the yield surface at whatever point it crosses. So now we want to explore the consequences of that normality rule, as we called it. Okay? So let me remind you. So to begin with, what do we show? We showed that the increment of plastic strain, d epsilon p, was normal, and I'll put in parentheses outward, right? We should have had to go outside the yield surface, to the yield surface. Okay, which the yield surface was defined as the level set, basically where the yield function is equal to 0. Okay, maybe I could also write it as reminding you that f is a function of whatever sigma is plus maybe some internal variables, right, equals 0. Okay, so don't forget that's our yield function. Okay. So we've stated what I want to sort of prove here, which is that the gradient of f points in the direction of the yield surface normal. So I want to show how we can know that. Okay. So let me write out what our goal is. Just say we observed that I think I stated without proof that the gradient of f, that vector, points in the direction of the outward normal of f. Okay? Okay, so we observed that. Now we want to show how. Now we prove this. Okay? Just so you don't have to take it on faith, or maybe you forgot stuff in Calc 3, or maybe you've just never seen this before. Okay, so to see this, we have to parameterize this curve. So we're going to consider the level curve represented by, and this is just going to be an arbitrary curve, f of x, y, and z equals c, some constant. Okay. So for our case, the constant is 0. Okay. So for our case, c equals 0. Okay. We're going to consider an arbitrary point P on this level curve. So let's say consider an arbitrary point P on the level curve. Okay. And if we represent that arbitrary point P, we would just say that P is equal to the point, let's call it x naught, y naught, and z naught, somewhere on that level curve. Okay. Now, we need to parameterize this curve in order to sort of develop our proof. So we're going to let a new function called r of t, and it's going to be a vector. So it's a vector valued function of some parameter. T, it could be time, it could be anything, but it's some parameter. Be defined. So let r of t be defined on the level surface or curve. So level curve such that r of t equals x of t, y of t, and z of t. Okay? So this curve r of t runs along the level surface and gives us the values x, y, and z that correspond to wherever we are on this level surface. Okay? Okay, now we're going to introduce a new function and just say, now let some function g of t, so let g of t be equal to f, the function f, of x and t, y of t, z of t. Okay? So this is now just some single-valued function of t. Because we know what f is, so because f is going to be equal to c, or 0 in our case, we may write the following, that g of t is going to be equal to 0, or how about c? Make that still be consistent. This is not specific to that value having to be 0. Okay, so now let's go ahead and just differentiate with respect to time, or to the parameter t. So differentiating with respect to t, we end up writing dg dt, and we end up using the chain rule, which is then going to be partial of f with respect to x times partial of x, dx dt, plus partial f with respect to y times dy dt, plus partial f with respect to z, dz dt. Okay? So hopefully that's pretty straightforward, and we also know what this equals to. Because it's a level surface, or a level set, and c is a constant, the partial of that constant going to be equal to 0. So let me now write this in a little bit of a different form. Let me say, in vector form, we could write the following. Okay, so I could say that dg dt is equal to the vector partial f with respect to x, partial f with respect to y, and partial f with respect to z, dotted with the vector dx with dt, dy dt, and then dz dt. Okay, that equals 0. And of course, we're doing this at some point p. So let me say that these are evaluated at some point p. And p, of course, is at t equals t naught, right? Whatever, that's what gives us the value of p. Okay? Right? And so we can, hopefully you see that here. If we dot this first term would be partial f with respect to x times dx dt, and so on and so forth. This quantity, what is that? That's the gradient of f, evaluated at point P. Okay? Well, what is this quantity? This quantity looks like r prime evaluated at t naught, right? What is this? What is this term here? If I parameterize a curve and I take its derivative with respect to that parameter, I actually end up with the tangent vector. So r prime of t naught is the tangent vector at P, the point which is equal to r evaluated at t naught. Okay? Okay. So what does that tell us? Okay, so now back to what we know about vectors. If two vectors have a dot product of 0, we know that they're orthogonal. And if this second vector is the tangent vector, then the gradient vector must be orthogonal, right? So what this tells us is, therefore, the gradient of f evaluated at the point, whatever point is on that curve, points in a direction that is normal to the tangent. Okay, so that's the proof. So that's and it's kind of important because what did we just say about the plastic strain increment in the previous lecture? Well, the plastic strain increment is also normal to that yield surface. Okay. So now we can say something about plasticity. So how about we may now write the following? We may now write that our flow rule, basically, which is that our plastic strain increment, d epsilon ij p, right? That was the quantity that we had originally was interested in, and was remember we had this quantity in our maximum dissipation postulate. That's going to be equal to some increment d lambda times the gradient of the yield function. Well, the gradient of the yield function, now going back into tensor form and out of vector form, is going to be partial f with respect to sigma ij. Okay? Let me just remind you, this is the gradient. I can put it in quotes if you like, because if you don't like the tensor gradient, but it's the gradient of the yield function. Okay? It's going to point in the direction normal to the yield surface. So, and we already said that we knew that this quantity also pointed in that direction, so they can only differ at most by some amount, some quantity, and we call that quantity d lambda. We could also write this in rate form and say that the plastic strain rate, right, which would just be taking the time derivative, basically, would be equal to lambda dot. There's some rate component, again, now multiplied times partial of f with respect to sigma ij. Okay? And we did define the following. So where we know what d lambda is, right, from about 4 lectures ago, maybe more than that. D lambda, we had an expression that looked a lot like this, where we had written out what the coefficients there would be. So d lambda is actually going to be our hardening function g, which we said was a function of sigma and q, our internal variables, times the quantity partial f with respect to sigma ij times d sigma ij, right? That's how we defined d lambda. We could also write lambda dot in a similar fashion and say that that is the hardening function g, and now partial f with respect to sigma ij, and instead of d sigma ij, this just becomes sigma ij dot, the stress rate. Okay, so that's why this was all important. That's what we did, was we basically justified a lot more rigorously now the form that we use for our flow rule. Okay, a couple observations. So here we're observing that f is not only a yield function, right? F is not only a yield function. What else is it? Well, right, this gradient term of f kind of keeps showing up. It also serves as what's called the plastic potential, which we also talked about previously. Okay? As the plastic potential. Okay? Therefore, the normality rule, okay, is also called the flow rule that's associated with the yield function. It's also called a flow rule that is associated with the yield function. Okay? If we have such a thing, then the flow rule of this type is called an associative flow rule, or associated flow rule. So then the flow rule is called an associative or associated flow rule. Okay? Now we can also have, so a flow rule that's derivable from a plastic potential that's distinct from F. So a flow rule derived from a plastic potential, and I'm going to call that potential G, distinct from F. Right, or what I really mean by that is that partial G with respect to sigma ij is not proportional to partial F with respect to ij. Okay, so partial F with respect to ij. So that's what I mean when I say distinct. Okay, if I have, so a flow rule derived from a plastic potential G that's distinct from F, which means that the gradient of F, when it acts in its plastic potential, is not the same, not proportional to the gradient of, the gradient of G is not proportional to the gradient of F, is called a non-associative or non-associated flow rule. Non-associative or non-associated flow rule. Okay? Okay? We call materials that obey an associative flow rule, we call those standard materials. Okay? So we call materials that obey an associative flow rule we call them standard materials. Right? And I want to, so let's try to think backwards here really quick. So why are they called standard materials? Well, what we began with was Drucker's postulate, and then we moved to a couple different postulates from there that got us to ultimately the maximum dissipation postulate. And from the maximum dissipation postulate, we were able to talk about the normality rule, which is what we just used here. So one of the things that Drucker was trying to do, and if you read the original papers, you see, is that he was trying to very carefully define stability. So standard materials are those that are going to be stable according to sort of the definition that Drucker gave, and so that's very common to sort of normal strain hardening materials. And of course, in the limit, we could talk about perfectly plastic materials. There are materials that have other behaviors than that, but they aren't stable in that fashion, don't follow Drucker's postulate, and so have to be dealt with with sort of a different type of potential here. And then we aren't able to say nearly as much about the consequences of that on the yield function itself. Okay. Okay, the final thing I want to talk about is I want to remind you, so let's just say recall the sign of d epsilon, and remember this is in vector form, in the case of a convex yield surface. So let me draw that picture again. So convex yield surface. Okay, so let me just draw a quick picture here. So here's our convex yield surface. Here's our location, right? We called that sigma bar. And we said that coming off of there is d epsilon p, that vector, and that would be tangent, right? Or sorry, normal to the tangent at that point. And what we just showed was that the normal in the outward direction is also given, or rather a vector that also points in the outward direction is the gradient of f, with respect to sigma ij. Okay, so So just note that both d epsilon p and the partial of sigma, and the partial of f with respect to sigma point in the same direction. Okay, and what the implication there is that gives us some bounds on lambda. That means that d lambda must be greater than or equal to 0, and the same thing with lambda dot. It must be greater than or equal to 0, right? If it's not, then we're going to have a plastic strain increment that goes into the yield surface, which doesn't make any sense. Okay, so that's sort of all the consequences that I wanted to talk about with respect to the normality of the strain increment and how that relates to the yield function, and then we'll move from there.